Welcome to this explainer. If you've ever set foot inside a science classroom, you've definitely seen the periodic table. It's almost always just hanging there on the wall, looking like this static poster of isolated facts, just a random, intimidating assortment of letters and numbers that you're forced to memorize, right? Well, today, we are going to completely shatter that perception. Because the periodic table isn't just some list, it is an incredibly dynamic, predictive machine of matter. And honestly, once you understand the engine running underneath it, the entire physical world starts to make perfect logical sense. So here's our agenda for today. We're going to cover 1, the evolution of the blueprint, 2, the core atomic engine, 3, the 4 pillar properties, 4, solving structural anomalies, and finally, 5, predicting chemical outcomes. All right, let's jump straight into section 1, the evolution of the blueprint. Let's look at the early history. Picture this. It's the year 1800. We've got a completely disorganized pile of just 31 elements and zero system for how they relate. Then we go through these wild experimental phases. You have Dauber-Reiner trying to group things into triads by averaging their masses. Then Champ-Courtois comes along and builds a literal cylinder. You even had Newlands trying to map elements onto musical octaves. It was just an era of pure trial and error. But eventually, this chaos led to Dmitri Mendelev's famous grid. Mendeleev brilliantly organized the 63 elements known at the time into 7 periods and 18 groups based on atomic mass. He even left intentional blank gaps for elements he just knew had to exist, like gallium and germanium. How cool is that? But here's the real plot twist. The ultimate paradigm shift, the one that actually gave us the modern table, came from Henry Moseley. While Mendeleev organized everything by atomic mass, Moseley ran these brilliant X-ray frequency experiments and proved that atomic number, literally the exact number of protons in the nucleus, is the true fundamental property of matter, not mass. Actually, scratch that, it wasn't just a shift, it was a massive leap forward that absolutely perfected the sequence. Moving on to section 2, the core atomic engine. Let's really dig into the mechanics of these elements. The modern architecture of our 1114 elements is so cleanly divided. We've got 7 horizontal rows called periods, moving left to right, and 18 vertical columns called groups, moving top to bottom. Now, as you move left to right, the atomic number goes up, but the outermost orbit, it stays the exact same. But when you move top to bottom, the atomic number increases and brand new outer orbits are continually being added. Within this master grid, elements are grouped even further into 4 specific structural domains. Think of them almost like different neighborhoods based on their electron configurations. We have the S, P, D, and F blocks. The S and P blocks together make up your main representative elements. That's everything from highly reactive alkali metals to totally unreactive inert gases. Then you've got your D block right in the middle containing the transition metals, which are super useful as catalysts like iron or nickel. And tucked down below the main table, just to save space, we have the highly reactive and radioactive F block inner transition elements. But hold on, before we can actually read this elemental dashboard, we really need to define the ultimate tug of war happening inside every single atom. This right here is the engine of chemistry. On one side, you have the effective nuclear charge, or ZF. That's the positive inward pull of the nucleus, physically dragging electrons closer. On the flip side, you have the shielding effect. That is the outward push caused by inner electrons literally repelling the outer electrons away. So, what does this all mean? Well, it brings us to our golden rule of atomic mechanics. As you move right across a period, those orbits remain the same, so the inward pull of the nucleus increases and wins the tug of war. But as you move down a group, the number of innermost electrons increases drastically, blowing up that shielding effect, which means the outward push wins. So remember this, inward pull wins going right, outward push wins going down. Absolutely crucial. Now for section 3, the 4 pillar properties. These are the core foundational traits driven by that engine. Our first pillar is atomic radius. Now, because electron clouds are fuzzy and don't have hard edges, we measure radius by looking at the distance between 2 bonded nuclei. And there's a very clear size hierarchy. Van der Waals interactions are the largest because the atoms just lightly touch. Metallic bonds are a bit smaller because they overlap slightly. And covalent bonds, those are the tightest because the atoms physically overlap to share their electrons. And the crazy thing is, size shifts dynamically the very second an atom gains or loses an electron. A cation, which is an atom that's lost an electron, shrinks dramatically. Why? Well, with a missing electron, that inward pull of the nucleus suddenly dominates.
On the other hand, an anion, an atom that gained extra electrons, swells up significantly because those new electrons crank up the outward repulsion in the orbit.
Let's move to pillar 2, ionization enthalpy. This is just a fancy term for the minimum energy required to steal an outermost electron from an atom. If we apply our golden rule, as you move across a period left to right, the atom shrinks and that inward nuclear pull gets super strong. Naturally, that makes it way harder to steal an electron, so ionization energy goes up. But if you move down a group, the atom gets huge. That outer electron is heavily shielded and far away from the nucleus, making it a breeze to remove.
Okay, section 4, solving structural anomalies. What happens when the expected trends suddenly break?
So according to that left-to-right rule we just talked about, you would totally expect boron and oxygen to have higher ionization energies than the elements right before them, beryllium and nitrogen. But no way. The actual data completely flips our expectations. Beryllium is mysteriously holding on to its electrons much tighter than boron, and nitrogen tighter than oxygen. What is going on here? What's fascinating is that quantum stability solves the mystery perfectly. Beryllium has a completely full 2s subshell, and nitrogen possesses this beautifully, perfectly half-filled 2p subshell. In the quantum world, perfect symmetry equals immense stability. They are stubbornly resistant to having that perfect balance broken by losing an electron, so it requires significantly more energy to remove one than the general trend would suggest. Let's dive into pillar 3, electron gain enthalpy. This maps the energy released when an isolated neutral atom finally captures an incoming electron. The energy economics here are super interesting. The first electron addition usually releases energy. It's exothermic, creating a negative value. But if you try to force a second electron in, you suddenly have to fight the sheer repulsion of that first newly added electron. It becomes endothermic, meaning you literally have to pay energy into the system. Overall, though, this value becomes more negative, meaning more energy is released as you move left to right. But wait, we hit another amazing anomaly right here between fluorine and chlorine. Fluorine sits higher up in the group, so technically it has a stronger inward pull. You'd logically think it releases the most energy when grabbing an electron, right? Actually, chlorine beats it. Why? Because fluorine has a tiny, cramped 2p orbit. It's like trying to shove a new piece of furniture into a tiny apartment. It causes intense spatial crowding and electron repulsion, paradoxically pushing the incoming electron away. Meanwhile, chlorine's spacious 3p orbit comfortably accommodates it. And that brings us to our final dashboard dial, pillar 4, electronegativity. Now, this isn't about capturing an isolated electron. This is about an atom's tendency to selfishly hog shared electrons in a bond. Measured on the Pauling scale, as electronegativity increases left to right across the periods, peaking at fluorine with a perfect 4.0, the element's non-metallic character directly increases right along with it. Simply put, the better you are at dragging shared electrons toward yourself, the more non-metallic you are. So the absolutely crucial takeaway from this entire master synthesis dashboard is this. Every single chemical property you observe, whether it's atomic radius shrinking, ionization and electronegativity spiking, or electron gain enthalpy becoming more negative, it is all merely a shadow cast by that one central tug-of-war. The whole shebang traces back to the precise balance between the inward pull of the nucleus and the outward push of the electron cloud. Which leads us to our final section, Section 5, predicting chemical outcomes. Let's map out some real chemistry. Because this incredible machine is organized by valence electrons into those 18 vertical columns, once you know an element's group number, you can mathematically predict its exact tendency to release or receive electrons. Group 1 will predictably always give up one electron. Group 17 will frantically try to steal one. This absolutely transforms chemistry from rote, boring memorization into crystal clear logical forecasting. When you combine elements from left to right with oxygen, the blueprint flawlessly maps the shifting architecture of the resulting oxides. It goes from lithium oxide in group 1, cleanly progressing step by step all the way to chlorine heptoxide in group 17. And the exact same perfectly logical divergence happens with hydrides, as hydrogen cleanly shifts its oxidation state when interacting with metals versus nonmetals. It's almost beautiful how perfectly it works. As we wrap up this explainer, I really want you to look at the periodic table differently from now on. It is not just a list of ingredients to memorize. Every complex reaction, every bond, literally every material in the universe is just this beautiful tug-of-war engine at work, mapped out perfectly on a grid. So now that you truly hold the blueprint of matter in your hands, The only question left is, what will you build with it?